All right, we are going to extend our understanding of finding roots. Um, we're going to extend it to complex roots. And in the last section, we used synthetic division and the rational root theorem and Descartes' rule of signs to figure out how many or what the roots were, but we didn't deal with imaginary roots. And imaginary roots always come in pairs. You can't just have one. If you only have one imaginary root, then the original equation will have an imaginary number in it. And we don't deal with equations that have imaginary numbers. So if I had the root x equals 3i, what is its pair? Negative 3i. And if I had x equals 1 plus 4i, then the other one would be negative 4i. So we usually just write it 1 plus or minus 4i. Okay? And some of these are really easy to find. For instance, x squared plus 9, the factors would be x plus 3i and x minus 3i, and the roots are going to be plus or minus 3i. Okay. What if I had 25x squared plus 16? What would the factors be? 5x plus 4i, 5x minus 4i, and the roots are going to be x equals plus or minus 4i over 5, or 4/5 I. Okay, let's do one more. 49x squared minus 1. 7x minus 1 and 7x plus 1. Good. That one is a difference of perfect squares, so it does not create i's. And the roots would be plus or minus 1/7. So a sum of perfect squares creates i's, and a difference of perfect squares does not. What about this? 16x squared minus 4x. Or plus, sorry. How do you factor that one? You have to pull a 4x out. 4x times 4x plus 1. There are no i's there. It's not a sum of perfect squares because 4x is not a perfect square. 16x squared is a perfect square, but 4x is not. So that one we would just use greatest common factor. Okay. If I had this information, I have a polynomial that is degree 7. Well, that's kind of big. Let's say degree 3. And I knew that the roots were x equals 1 plus 3i and 6. Can you tell me what the other root is? 1 minus 3i. Does everybody understand that? Okay. If I told you I had a polynomial of degree 5, and I knew that the roots were 4i, 1, whoa, don't know what I was doing there, 1 minus 3i, and 7, can you tell me what the other two roots are? So negative 4i and 1 plus 3i. Does that make sense? Every complex root has a conjugate pair. They always come in pairs, and they have to be conjugates. If they're not, when you multiply them together, the i's don't cancel. Okay? What if I had a polynomial and I knew that the roots were 3 and 2i? Could you tell me what the equation is? Well, I need the other root. The other root is, 1 One's negative, one's positive. Okay. And what are the factors there? X plus 2i times x minus 2i. And I'm going to multiply those out one time, just so you can see what happens. X squared minus 2xi plus 2xi minus 4i squared. But the xi's are opposites, and they cancel. I squared is negative 1, right? So it turns into x squared plus 4, but now I have another root, x minus 3. I don't know where you're getting 9 from. If it was 3 and negative 3, then we'd end up with a 9. But we only have one real root. Now I multiply again, and I get x to the third minus 3, x squared plus 4x minus 12. Does that make sense? Okay. What if I had the roots x equals, we're going to make this kind of small, 2 and 3 plus or minus 5i. My factors are x minus 2 and x, what would the next factor be? Minus 3 minus 5i and x, nope, x minus 3 plus 5i. If I set both of those equal to 0, x equals 3 plus 5i and x equals 3 minus 5i, I need to move these over and these over. And in both cases, the 3 is going to be negative. So x minus 3 minus 5i and x minus 3 plus 5i. And that negative right here is where people make mistakes. But it has to be the opposite of whatever the root is. All right. Now, should I multiply those together? No. Always multiply the conjugates together because it's going to simplify. It will work if you multiply in by x minus 2, but you're going to get a long equation that has lots of i's in it, and then the next round of multiplication is going to be really confusing. So, x squared, and then negative 3x. Do I need to multiply those? X times 5i. Is there an x times negative 5i later in the problem? Yes. So I can skip that. In fact, you can skip every I multiplication except I times I. So what I'm saying is, this multiplication right here is opposed by that multiplication right there, and they're going to cancel. And this multiplication right here is opposed by that multiplication, and they're going to cancel. But you do need to multiply the I times the I. You can skip every I multiplication except the last one. You'll have a positive version and a negative version, and they're going to cancel. And that's why complex roots always come in pairs. If they're not conjugates, then the i's don't go away. So you can't have a parabola with x equals 2i and x equals 1 minus 6i. Because when you multiply those together, the i's don't cancel. So I skip, let me get rid of some of those. So I skip this multiplication, and then I move on to negative 3x plus 9, and then I can skip that multiplication because it's going to cancel. Then I move on to the negative 5i. I can skip that one, and I can skip that one. But I need the last one. Negative 5i times 5i turns into negative 25i squared, but I squared is negative 1, so it turns into plus 25. And this is the pattern every single time. You're going to get 2 copies of that, and then you'll get the middle term squared, and then you'll get the last term squared. That will always happen when you do complex conjugates. We end up with x squared minus 6x plus 34, sorry. Now, what do complex roots tell me? If I have the equation x squared minus 6x plus 34, and I know that the roots are 3 plus or minus 5i, good. Because the roots are complex, we know that the graph doesn't touch the x-axis. Okay, in this case it's above. All right, but what does 3 plus or minus 5i tell me? Well, I have a parabola that's going to be way up here pretty high, right? If I flip that parabola upside down, okay, I flip it upside down. Ooh, that's kind of a bad picture. Hang on. So if I flip it, oh, I did it again. So let's do like this. If I flip that parabola upside down, it's going to hit at the same place it would hit if I got rid of the I. 3 plus 5 is 8, and 3 minus 5 is negative 2. So if you take that parabola that doesn't hit the x-axis and you flip it upside down along the vertex, and you eliminate the I from your roots, you'll end up with 2 x values, and that's where the graph is going to hit. That gives us a good idea of where the graph is. If we know that it hits at 8 and negative 2, we know that the vertex has to be in quadrant 1. It's further to the right than it is to the left. Okay. Another thing is, if I were to eliminate this number, then I would get x squared minus 6 plus 9, and that has a duplicate root at x equals 3. So if I change this to a 9, then the parabola would look like this. And all I did to that graph was lift it up 25. What I'm saying is, if you get rid of the 5i, then we would have a duplicate root parabola at x equals 3, and that 5i just lifted the graph up 25. So that's kind of how imaginary roots coordinate with regular quadratics. Okay. All right. Now I need to take this, and I need to multiply it by that term. X minus 2 times x squared minus 6x plus 34. X to the third minus 6x squared plus 34x minus 2x squared plus 12x minus 68. X to the third minus 8x squared plus 46x minus 68. And that would be the parabola that has one real root at 2, and then the imaginary roots 3 plus or minus 5i. All right. Okay. So the first set of problems is pretty easy. And then we get to, what's that? I'm on 304. The next section is a little bit more complicated. Look at number 24. Number 24 on page 304 says x to the fourth minus x to the third plus 7x squared minus 9x minus 18. And it tells me that x equals 3i. And I am supposed to find all the roots and write the polynomial as a product of linear factors. Okay? Well, I know that one root is 3i, so the other root must be negative 3i. So I'm halfway there. I know x equals negative 3i, and as far as the factors go, x minus 3i and x plus 3i. How do I find the other two? Good. I need to use division, but I can't do synthetic division with an imaginary number. I can't do long division with an imaginary number. There might be a way to do it, but nobody does. Okay? You take those two imaginary roots and you create a quadratic. What quadratic does x minus 3i and x plus 3i create? X squared plus 9. So I know that x squared plus 9 is a factor of the original x to the fourth polynomial. Now I do long division. There's a trick though. The x squared plus 9 is missing an x. So we put x squared plus 0x plus 9 in the box. And I don't know how many columns there are going to be, but I do know that the remainder is 0. So that should make things a little bit easier. What do I put in the first square? X to the fourth. So on top I get x squared. Now I use that x squared to finish the column. 0x to the third and 9x squared. Now this box and this box need to add to be negative 1. Negative 1x to the third, which gives me negative 1x. 0x squared and negative 9x. This box and this box and this box need to add to be 7. I need to subtract 2x squared. So negative 2. And now I should end up with the two numbers that I'm left with. So 0x and negative 18. This box and this box need to add to be negative 9. And they do. And this box needs to add to be negative 18, and it does. I'm now left with the quadratic x squared minus x minus 2, which factors into x minus 1, x plus 1 and x minus 2. Those are my factors. And my roots are 2 and negative 1. So there's no, well, yeah, there's no guessing in this set. Well, the next section that we'll do tomorrow is a little bit harder. But today, all you have to do is take a polynomial, take an imaginary root that you know and create the other imaginary root, turn that into a quadratic, and then long divide. So I want to do one more. Let's do 34. X to the fourth minus 7x to the third plus 14x squared plus 2x minus 20. And I know that one of my roots is 3 plus I, so the other one must be 3 minus I. What quadratic is created with 3 plus I and 3 minus I? We need to multiply x minus 3 minus I and x minus 3 plus I. And I can skip every multiplication that has an I in it except the last one. I have to hang on to the last one. X squared minus 3x minus 3x plus 9 minus I squared, which turns into plus 1. And that might seem complicated, but remember the pattern. you always get 2 copies of this, and then the middle term squared and the last term squared. So the more you do these, the less you're going to have to think about what the quadratics really are. That yields x squared minus 6x plus 10. Now what? Now I use long division to simplify this into a quadratic. X squared minus 6x plus 10. This is x to the fourth, x squared minus 6x to the third, and then 10x squared. This one and this one need to add to be negative 7, minus x to the third, negative x, plus 6x squared, minus 10x. This one, and this one need to add to be 14. I need a negative 2x squared. That will give me negative 2, and then plus 12x, and negative 20. This box and this box need to add to be 2, and they do. And this box needs to be negative 20, and it is, so there's no remainder, which we knew, but now we know we did it right. And I'm left with x squared minus x minus 2. Oh, we just did that. So my factors are x minus 2 and x plus 1, and then my roots are 2 and negative 1. Does that make sense? Now, if you look at the section that starts with 35, we're going to be doing exactly the same thing, but they don't give us a hint. That's for tomorrow. Well, we know the hints, right? We know the rational root theorem. We know which guesses to use. We know the Descartes rule of signs. We know how to simplify using synthetic division. So we are doing 304A. One through 30, is it 30? 33 odd. (304A) 1 through 33 odd. All right, good luck.